Good afternoon and welcome to the Embedded Executive Podcast. I am Rich Nass. I am with Embedded Computing Design, and my guest this week is Shawn Hymel, and he's an expert in TinyML, which is a topic that we have not given enough coverage to on the podcast here. So that is why I invited Shawn. Um, because as we get more into TinyML or ML in general and AI, there's just a lot of disconnect where people understand uh, what's happening, what's production ready, what's still hype out there. So I want to talk to Shawn and really get, a reality check on where this technology stands. So how you doing, Shawn? Let me start there.
Yeah, I'm doing fantastic this morning. I really appreciate you having me on the podcast, and I'm excited to chat with you about TinyML and hopefully help people understand where this technology is going, and how does it relate to this whole AI movement at large.
So a little bit of background on you. What's your expertise? How did you get into TinyML?
Sure, I mean that goes back to my grad school. So I graduated undergraduate with a degree in computer engineering. A few years later, I got my graduate degree in electrical engineering, but they had me analyzing signals in order to classify them based on hidden Markov models. And the funny thing is, I wrote these programs. I was doing bare CUDA at the time to try to parallelize these algorithms to train these hidden Markov models to identify these signals. I mean, this thesis just sits in a professor's drawer somewhere collecting dust. It didn't go anywhere. But I had no idea at the time I was doing machine learning. That's basically what I was doing. We just didn't call it that because the CS people did machine learning. We were doing signal analysis, right? It's just very different. But in reality, it's training these mathematical models in order to try to take some input and approximate some output. That's all it was doing. And it's just automatically updating parameters. We just weren't using neural networks, which are all the rage right now. So I was super interested at the time. I just didn't know what it was called. Fast forward years later, I worked for SparkFun and I start hearing, what was this, 2015, 2016, we start seeing these early trickles of, hey, AI is beating these records. It's finally coming to the forefront of computing. And I'm thinking to myself, everything we see in the embedded world is what the CS people are doing on big computers in about 10 years later. So I knew this was coming. So I started refreshing myself on machine learning. I was like, oh, right, this is what I was doing in my graduate program. It's just we're using neural networks instead of HMMs. Go figure. And so I fell in love with doing the machine learning side. If anybody's curious, if you want to brush up the Andrew Ng's courses on Coursera, they walk you through the math of neural networks. Highly, highly recommended. Just get up to speed on those to see what this is all about. And then once that happened, I started playing around with, at the time, there was TensorFlow Lite for microcontrollers, was kind of this niche project within Google under the TensorFlow umbrella. And I got things running on microcontrollers. It was really cool to see to do really basic stuff. I'm talking things like keyword spotting, things like your ALEXA, if anybody's listening to this on such a device, that's doing keyword spotting on a microcontroller. I mean, that might be changing in the future. Your SIRI is also doing it on your phone. They're all doing it basically TinyML, which is just running these machine learning algorithms on microcontrollers on these little processors. And we could get it working on like ARM Cortex M3s and ARM Cortex M4s to do really basic stuff. Think like gesture recognition, barely any sort of image processing. I mean, maybe you could get face, not face in a like 28 by 28 grayscale image. It's real basic. So I started playing with that as I developed more content around that because I was contracting with DigiKey to make these videos. Edge Impulse reached out. I knew some folks there, went to one of their events, worked with them to teach a course, and they eventually invited me to work with them full time. So I did that for a few years, going around basically doing this, teaching, getting people excited about this TinyML movement. Eventually becomes under this umbrella of Edge AI, where Edge AI includes things like running AI algorithms on your smartphone, on your laptop, and microcontrollers. So everything outside of the cloud. So TinyML, there was a TinyML Foundation. It's now the Edge AI Foundation. So you'll see this TinyML terminology becoming assimilated into this Edge AI umbrella. But we still talk about TinyML of running machine learning algorithms, generally just inference. You're probably not training on a microcontroller on these little microcontrollers. We're running inference on these microcontrollers, but now we're getting things like NPUs, which are your neural processing units that are very specifically configured hardware, usually as a co-processor on a larger, more beefier, say ARM Cortex. What do they like? The M4s or M7s now. And they have an ARM has its own Ethos core that will do accelerated neural network processing for this inference. And now we're running things like full object detection. There's these stripped down versions of the YOLO models that we run on these. So I'm just trying to keep up to speed because things are changing fast. Everything you saw 10 years ago in the CS world in machine learning land, we're now getting on microcontrollers. And it's super wild to be a part of this.
Are the processors at the point where they've caught up to the TinyML technology and they're actually pushing the barriers and they can do a lot of these things on their own because of the way they've been trained lately?
Are you talking about the models themselves?
Yes.
So somewhat, a lot of times we have machine learning folks who don't care about process, right? They just assume you have infinite process capabilities in your hardware. And so they love to do things like,
But
oh,
that's not
hyperbolic.
true.
Sometimes, I mean, the good, right? The ones who exist low level will develop these algorithms and pay attention. But a lot of times the computer science people, they're like, oh, we're going to do hyperbolic tangent activation functions because that makes sense for the math. And you're like, that's so hard in compute. You're burning so many cycles. So you're right. There are some people who are looking at, converting that. Can we use ReLU, basically just, everything that's negative becomes a zero. Can we do that and get some nonlinearity in there? And hey, it works. And you might lose a little bit of accuracy, but it works so much better in modern day processors, including microcontrollers.
Okay. It sort of dawned on me, why aren't you locked in a room somewhere working for one of the major manufacturers, just engineering this stuff?
I enjoy the teaching side far too much. As much as I like working on developing these algorithms, I am absolutely fulfilled by the teaching side. So I kind of build myself as this corporate professor, where I contract out to make educational videos, educational content, flying around teaching workshops. I find that more fulfilling to me personally. And I've done the corporate engineering side for a little while. I'm drawn to that, public facing side.
Okay. Has TinyML run its course? Are we looking for the next best thing, or is there still some runway there?
I think that TinyML, that's kind of a dying name, but the idea of it has not run its course. We are seeing new technology come out embedded all the time. I mean, even if it feels like algorithms are behind the, cloud world, that's okay. Things like smart doorbells, self-driving cars. You look at like satellites, you look at what else do I have around me? Any sort of like keyword spotting stuff, anything in your home, the smart thermostats, a lot of these where, you need on-device inference because you can't assume connection to the internet, or you can't survive the latency. You need processing done right now, or you don't want to just stream infinite video because that hogs your entire network's bandwidth all the time. We can do a lot of stuff on the device now, especially with things like NPUs, and get those results so that the idea of IoT becomes streaming these inference results or some sort of post-processed inference results after the machine learning or after inference is done on the device itself. If you need bigger stuff, right, we're not talking about running LLMs, although there are people who are trying to run these large language models on these devices. But for the most part, that's a cloud computing problem. So can we use the smaller devices to run smaller machine learning algorithms to solve the problems, right? Embedded is usually just, can we solve these niche problems? We make a microcontroller that does one thing or two things very well. And I think TinyML is perfectly fit for that, right? We're training these models that do this one thing. There was one I read about, I think it was Prague, and their escalators. They're trying to, or did, deploy small devices that you basically slap to the side of an escalator, and it listens for and records vibrations and does machine learning in the sense of inference, but it's a basic form of sensor fusion, right? It's a learned sensor fusion that looks for anomalies to see if the escalators need repairing. right? Do they
Hmm.
not sound right and vibrate right? And I'm going to notify. And, that's just, once an hour, it just pings some network. Think MQTT being like, all normal, or hey, send somebody out to check this out. Something's not normal with this escalator. So I think something like anomaly detection, I call this, kind of a silent thing in IoT, industrial IoT, where industry, smart cities, things that you don't realize, you don't see every day in the home, they are adopting new technologies to try to do things like anomaly detection, because we get into the world of predictive maintenance. And if we can, find something's going wrong in a machine, a car, an engine, a satellite before it actually breaks down, that's a much easier time to maintain it and fix it. And machine learning is absolutely helping there. Even, even really basic things like k-means clustering, right? This is now part of the machine learning world. So if you're doing k-means clustering, surprise, you're doing machine learning.
Are you finding that it's accurate enough to do these applications that you're talking about? This anomaly detection. Um, a false positive is a bad thing. And are you seeing that it's accurate enough today?
It absolutely depends on what you're trying to do and where your threshold and your tolerance is. I mean, that's the case for just about anything. And that's something I think makes a lot of embedded developers uncomfortable, is working with this idea of non-determinism. So in most cases, the actual process of inference, if we're talking about a neural network, it's a bunch of multiply and accumulates and nonlinear functions. If I give the same input, I get the same output. It is technically deterministic. But because there's so many variations that you can get for any sort of input, we generally have to treat it as some type of stochastic or probabilistic information going into the network or into our algorithm. And so you're right, we get false positives and false negatives. And a lot of times you can adjust your threshold for what you're comfortable with. So, you're looking for precision and recall, right? Like, can we adjust that curve to we're okay with more false positives and not okay with false negatives? So adjust your threshold here or adjust your threshold in the opposite
Hmm.
direction. And it really depends. It's how much time, compute power you have in order to make something that works for your particular needs. This is not a deterministic thing where like I have an input and I'm going to always turn this motor or whatever. It's no, I might get some false positives, and where are we okay with this? Or I might get some false negatives and vice versa.
Hmm.
So it becomes this kind of gray fuzzy area that I think makes some people uncomfortable, because it's hard to work in that and wrap your head around what does it mean to be probabilistic when you're so used to working with determinism.
What about the comfort level of TinyML in general? Are you finding people are really getting their arms around it these days, or is it something that people are still afraid of?
I don't see a lot of fear. I see a lot of people going, where is this useful? And in a lot of cases, I hear people talking about it, and it looks like a hammer in search of a nail. I will absolutely admit to that, right? We do the magic wand gesture, like, that's so cool. That's neat that we can do that on a microcontroller. Where can I use that to solve a problem? And I think that's the issue we're seeing. So I listed a few potential applications, and I think the biggest nut to crack is going to be industrial IoT. The idea of, can we do things like anomaly detection, and can we do things like automated part counting and automated optical inspection? Can we make these processes better, more accurate for people than the current technology? Because as you have things rolling off the assembly line, can we help in ways that automate things like, hey, there's a defect here? There's a lot of research going into that, and it's just things we don't see, right? I think back to the early IoT days, 10, 15 years ago, everyone was talking about this crazy connected home, smart devices, blah, blah. Like, my printer's barely connected to Wi-Fi. So, right? I mean, I don't have a smart thermostat. I know lots of people do and they love them, but I don't have a whole lot of, smart home things. I refuse to connect my refrigerator to the internet, even though I work in this field, because I think it's just absolutely ridiculous.
Hold that thought. I want to come back to that, but
Sure.
you you said industrial IoT is a harder nut to crack. I think those are the words used. Why? I would think that that would be an easier place.
Easier in the sense of market. So I think there's a lot of marketability. If you can say, uh, my dream idea here is to have just some arbitrary device, and I can just walk up to any assembly line, any turning motor, any robot arm, anything with a motor or a bearing, slap a device to it, I push a button, it listens for a couple of days, and it just automatically, whatever you need to do, send it to the cloud for training. It collects data, trains a model, redeploys a model back to the device, and goes, aha, I can now tell you when this device is starting to act a little funny using whatever algorithms you want, right? This could be a neural network, this could be k-means clustering, blah, 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 but it automatically learns the device. Now, this is still a somewhat technically difficult problem. OTA, over the air updates, is solved, but tricky for people to deploy en masse, right? Just in general, getting a lot of that out there. Doing things like individualized OTA, doable, but tricky. And then collecting enough data to train a model that the operators are comfortable with, also technically tricky. So I think this is going to be a thing. I mean, or these devices are deployed with, right? My hope is like you can have a device that just sticks to some legacy because nobody wants to upgrade their equipment. But I think going forward, devices are going to have these algorithms built in, and we may not need full TinyML. A lot of these machines run on full computers, and we just make it part of it, right? Can we listen, just add sensors, and now we have it as part of the total software. But I think like PLC or these legacy assembly lines where can we stick something to it, use TinyML to automatically update. I think the market is likely there. I mean, forgive me, I don't work directly in the IoT realm, so I'm sure one of your listeners will have better insights to it, but that's kind of where I imagine this idea of TinyML going.
All right, let me take issue with you now.
Yeah.
Our folks who are regular listeners know that I tend to be a leading edge guy. My house is about as automated as I can get it, from my garage door openers to my pool filter and everything in between. Why aren't you in the same camp? Why isn't everything in your home automated? You're supposed to be somebody preaching the technology. What's
I know.
up
I
with
don't.
that?
Yeah. Do what I say, not what I do. Right. I
Why?
How do I put this? I would say I'm closer to a mainstream adopter and not an early adopter of a lot of tech. I generally want something to guarantee to work if it's going to be brought into my home, and it has to be game changer enough for me to buy into it. So I do have a smart speaker. It's in the kitchen. The
Being
game
able to sit on the couch and do anything you want without having to get up, that's not game changer enough.
I mean, I could tie it into the lights. Man, but like, there's also the idea of the security of exposing more surface area for attack vectors, right? Like, could somebody get in my, and I read about these things of like nanny cams running Linux with just default username passwords. And I'm like, I would hope I'm smart enough to change those passwords. But if I bought a nanny cam, my thought would be like, oh, it's a microcontroller. There's no login. And I would be totally wrong. So, right, I don't dig into it enough a lot of times. So I'm like, I don't trust whatever it is I'm connecting to my network right now as my default state, unless it's like I'm willing to expose myself in certain ways that give me the benefit. So smart speakers, I just got rid of my Alexa because I didn't like their new terms of service. And I got a Siri, which is decidedly worse, but I agree with Apple's security stance a little more. Right? That's that, and the smart doorbell, because the house came with one, is probably like the most leading edge home tech that I have. I would like to get a smart thermostat because I love the idea of it learns over time your different habits and can hopefully save you energy. I don't want to give that information to Excel. I don't like the idea of the energy company going, you know what, we're going to make your house hotter today. I like that's their new thing. The energy company where I live, they're like, oh, we'll install a free smart thermostat, but we can adjust your temperature whenever we want. I'm like, I'm not okay with that. And I never bought a Nest because I was like, this is a startup and I want to see where this goes first. So I gave it a year or two, and sure enough, Nest did not survive. So I wait until stuff is going to have longevity before I invest into it. Now, if I had the time, I would love to have personal projects where I'm like, I'm running this Raspberry Pi and I'm connecting all these things. I just recognize that's going to eat up a ton of my time, and that becomes a project, not a solution to a problem.
I agree completely. I'm actually in the middle of one of those projects where I'm designing a face recognition to put at my front door to unlock the front door when it recognizes the people. But it's taking me a little longer than I would have hoped to do it. But I will get it done.
So let me ask you this. If I print out a picture of your face and I walk up to your doorbell and hold it in front, will it let me in your house?
TBD. I'll let you know.
Okay, you gotta test that one. That would make me
Absolutely.
very. I love the idea, but I'm like, I mean, to be fair, somebody could walk up with a lock pick set. But having tried it myself, like on my own door, I'm not trying to pick other people's locks. Those basic ones that lock the handle,
Yep.
totally useless. You can pick those in like 5 seconds. Deadbolts, way freaking harder. So I am like a big fan of just basic key and a deadbolt for a lot of stuff.
Yeah, well, and in my case, where we live, we don't ever use the front door anyway because we just come and go out of the garage. So
Fair, yep.
so it has limited use. But anyway, but I digress. Anyway, this is really interesting stuff, Shawn, and I appreciate you coming on. And I'd love to do this again as we advance the technology a little further.
Yeah, absolutely. I really appreciate you having me on, and this is such a fun moving field to discuss.
Absolutely. That was Shawn Hymel, and I am Rich Nass with Embedded Computing Design. Thanks, Shawn.
Thank you.